Okay, so one more example of a problem involving parametric equations. An object moving along the curve in the xy plane has position x, comma y at time t with dx dt equals cosine of e to the t and dy dt equals sine of e to the t for 0 is less than or equal to t is less than or equal to 2. At t equals 1, the object is at 3, 2. So what I'm given is a horizontal velocity, a vertical velocity, a time interval, and an initial position. Sort of initial position. It's not actually my initial position, but it's my position at t equals 1, which should be some information that can help me. So first question is, find the equation of the tangent line to the curve at the point where t equals 1. So what do I want? I want the equation of tangent line at t equals 1. So how do you find the equation of the tangent line? Well, basically you need dy dx at t equals 1, and you need a point at t equals 1. Well, lucky for me, I already have a point at t equals 1. It's 3, 2. So all I really need is dy dx at t equals 1. Well, I don't have dy dx, but I do have dx dt and dy dt, and I know in parametric equations that dy dx is equal to dy dt divided by dx dt. So a formula for dy dx would simply be sine of e to the t divided by cosine of e to the t. And if I want this at t equals 1, I can plug in 1 and get sine of e divided by cosine of e, which I could write as tangent of e. So sine of e, cosine of e, that should be tangent of e. So that is the slope of the curve at 1. I've got the slope, I've got the point, then simply my equation should be y minus 2 equals tangent of e, whatever that is, times x minus 3. And that's it. That's the equation of the line tangent to the curve at t equals 1. Again, anytime you want a tangent line, you need a point, and you need dy dx, the slope of the curve. I found dy dx by dividing dy dt by dx dt, plugging in 1, and then I just used point slope form. Next question is, find the speed of the object at t equals 1. Speed is simply given by want speed. It's simply given by the magnitude of the velocity vector, or the square root of dx dt squared plus dy dt squared. And I want it at t equals 1. Well, let me not forget that I already have the vertical velocity at 1, horizontal velocity at 1, right? I'd already found those to find the slope of the tangent at 1. So at 1, I should get the square root of cosine squared e plus sine squared e, squaring that and squaring that. But cosine squared plus sine squared is just 1. So this is the square root of 1, which is 1. So the speed at t equals 1 is just 1. That works out quite nicely. Find the total distance traveled by the object over the time interval 0 to 2. Well, total distance, you integrate speed dt. So 0 to 2, my speed, which is simply the square root of dx dt squared plus dy dt squared, which should be cosine squared of e to the t plus sine squared of e to the t dt. Again, cosine squared plus sine squared is 1, so this becomes the integral from 0 to 2 of 1 dt. Imagine that. Do I know how to find the antiderivative of 1? Yes, I do. It's t. So that becomes t evaluated between 0 and 2 using the first fundamental theorem of calculus, which is simply 2 minus 0, which is simply 2. This thing has traveled 2 units in those 2 seconds. Again, the important thing being you integrate speed dt, little bits of speed, little bits of time to get your total distance. And because cosine squared plus sine squared is 1, this becomes a very simple integral. Finally, find the position of the object at time t equals 2. position of the object at time t equals 2. Well, I know the position at 1. I want the position at 2. I know how quickly it's moving horizontally and vertically, and so what I'm going to remember is that if I find the integral of vertical velocity, I should get change in vertical position. Yep. And if I find the integral of horizontal velocity, I should get the change in the horizontal position. So if I know I'm here, and then I can find the change between 1 and what I want, which is 2, I should be able to figure out where I ended up. So what is that going to look like? It's going to look like started at 3, then changed this much, right? This is the change in horizontal position between 1 and 2. So this should give me my answer, which would be x of 2. Okay? And vertically, I started at 2 at 1. If I add on the change in position, vertical position, between 1 and 2, which is just the integral of the rate, I should get y of 2. And once I have x of 2 and y of 2, I've got my position at time 2. Just thinking about this in terms of the first fundamental theorem of calculus, I'm going to erase this. Let's remember that when you want to find position and you're given velocity, write an integral from where you know to where you want. We know the position at 1. We want the position at 2. Let's pop our velocity in here, in this case horizontal velocity, and I know, using the fundamental theorem of calculus, that this has to be x of 2 minus x of 1. Similarly, for vertical, I would just plug in my vertical velocity here, and I would get y of 2 minus y of 1. But then I know what x of 1 is. It's 3. So I can replace x of 1 with 3. And if I add it to the other side, I get that equation right there. That my final position, x of 2, is simply equal to my initial position plus my change in position. So that gives me those two equations. I could write something similar, again, for vertical velocity, and say that if I integrate vertical velocity from 1 to 2, I should get the change in my vertical position. But since I already know what it was at 1, that's why I chose 1, because I know the position at 1, I can replace this, y of 1, with 2. If I add 2, I get 2 plus the change equals my position at 2, which is exactly what I had here. Now, you'd have to use a calculator to find this, because sine of e to the t is not a function that we know how to integrate. But that takes care of this lovely problem.